In the last lecture, we saw what are oscillators, and we saw that these are of two types based upon the working principle. First is relaxation oscillator, second is linear, which is also called feedback oscillator. So we have already studied one example of relaxation oscillator. In this lecture, we will study linear oscillators, which are also called feedback oscillators. And these linear oscillators will be implemented using R and C, in addition to, of course, op-amp. That means active elements will also be there. In the next class, we will see LC-based linear oscillators. So first, we will see what is the general model of a linear oscillator, and then we will use that model to derive the necessary condition for oscillation. And then we will also point out why it is called linear or feedback oscillator. So let us consider two linear blocks, A and beta, connected in this fashion. That means output of block A is fed back to block beta, and then the output of beta is added to an external input. So sum of these two produces VE, and the output of beta will be called as VF. So here what we have is VE is equal to VI plus VF. And these two blocks, block A and block beta, they are linear. So we can write their output as A into VE and VF as beta into VO. So this is equation 1, this is 2, this is 3. Right. So here we would like to know what is the output in terms of the other quantities, especially input and A and beta. So we want this output to be finally expressed in terms of input. So we start from equation 2. So we find that 2 and 1, they imply VO is equal to A into VI plus VF. And then from 3, we can eliminate this VF to get VO is equal to A into VI plus beta into VO. And that will give us 1 minus beta A into VO is equal to A into VI, or VO is equal to A into VI by 1 minus beta A. So we now know what is the relation between output and input. So what we have here is a network consisting of two blocks, but what we want is we want a single block relating the input with the final output and the individual blocks transfer function. So this is the relation that we have got here in equation 4. So here you can see that we have a block So this equation 4 basically represents a block which has Vi and Vo, and this is A divided by 1 minus beta A. But if you want this circuit to act like an oscillator, so for oscillator, we know that Vi should be 0. That means oscillators are single port blocks or networks. They only produce output. They do not take any periodic input. They may definitely, or in fact, they will always take DC input. So now what we want is to get rid of this Vi, right? So here in the limiting case, we can see that if we try to reduce Vi gradually and make it 0, and if we want this output to be finite, then we definitely need to reduce the denominator also, right? So in the limiting case, what we find is that when Vi is made 0, 1 minus beta A should also be made 0 for finite output. So we say that if you want to have a block where there is no input and we want finite output, and the block consists of two networks beta and A, then the condition that must fulfill for finite output VO, which implies sustained oscillation, you will see that this condition is impossible to fulfill at all frequency. So that is why what you will get here at the output side is going to be a periodic signal consisting of particular frequency. So for sustained oscillation, what must get satisfied is this equation. So this means beta A should be equal to 1. And in more explicit way, we can write or so this is called Burkhausen criteria. We will see that this equation 5 basically leads to two equations, because this is a complex equation. That means left hand side in general will have real and imaginary part. So this equation 5 implies two equations. First is you can say that real part of beta A is equal to 1, and second equation is imaginary part of beta A is equal to 0. So this is one way of representing this, or equivalently magnitude of beta A is equal to 1 and its phase is equal to 0, or of course 360 degree or its multiple. So these are the two ways in which equation 5 is represented. So that is why this is called Birkhausen criteria. And equation 5 is necessary condition. So that means if you find a circuit which is oscillating, that means if it is producing output without any external periodic input, and if you investigate, you will find that this condition is getting fulfilled. However, reverse is not true. This is not a sufficient condition. That means if you have a circuit where this condition gets fulfilled, then there is no guarantee that it will be able to produce periodic output without any external periodic input, right? So, so keep this fact in mind. And since this is not sufficient condition, actually, as a designer, we would like a sufficient condition because that would guarantee that what I want will happen. So as a designer, we want sufficient condition, which is not easy to derive in general for oscillators. But still, this necessary condition itself is very useful, and it helps a lot in designing circuit related with oscillators. So here it was pointed out that the oscillators that we are going to study in this lecture, they are linear. So that linear oscillator name comes from the linearity of the two blocks that have been used here in the model. And because there is a feedback involved, that means output is ultimately fed to the input side of the network. So this is also called a feedback oscillator. So these are the two names, and the third name, as was pointed out, is sometimes called sinusoidal oscillators. We will see that this output is going to be sinusoidal, and that happens because this equation 5, this will usually get satisfied at one particular omega. So that will imply that there is a one sinusoidal output for which this equation 5 get fulfilled for the circuit that we have set up. So that is why this circuit produces sinusoidal output, and it is called feedback or linear oscillators. Now, as was pointed out in the title of this lecture, that we are going to consider RC version of the linear oscillators. That means there will be two passive element only resistors and capacitors, and of course op-amp will be there. So we are now going to consider two circuits, RC based oscillator circuits in this lecture. So first we will talk about a very well known RC based circuit, that is Wien bridge oscillator. So it is named after this person Wien. Later on we will point out the importance of this word bridge, and we will use it also to analyze or reanalyze the circuit. But first we will take up the feedback model that we just studied. And one more thing I would like to point out here before we proceed for the Wien bridge oscillator. So keep in mind that we obtained this equation 5 for 0 external input. So the model gets simplified to this model, that is output is connected to beta network. This is called feedback network because it is through this network that the output actually reaches to the block A. So here we see that there are only two signals, VO and VF. There is no VI. VI is 0, so VE has become equal to VF itself. So the circuits, two circuits that we are going to study in this lecture, they will can always be represented or molded or casted into this simplified model of the oscillator. So first we will see the circuit. So it consists of one op amp, and output is actually the output of this op amp. And here we have inverting mode configuration. Registers R2 and R1 with the negative feedback path. Now this op amp, so here you can see that we have 0 here. That means signal must be fed at somehow at the positive terminal. That means it is basically working in non-inverting mode. So here we take a network consisting of resistors and capacitors, first in series and then in parallel. And voltage produced by these, this is then connected to the positive terminal. So this is the Wien bridge oscillator. Now here we must mold or cast it into the feedback model that we have just now discussed. So here you can see that block A, as the name also or the symbol also suggests, is basically an amplifier. So here this much portion of the circuit is block A, and the rest of the circuit is feedback block. So you can see that we have output, and the output is then sensed by this feedback circuit, and it produces voltage Vf, which is being fed to the amplifier, and then amplifier amplifies it to produce the final output. So we have to use that Birkhausen criteria equation, that means equation 5, A beta is equal to 1, to see what happens at the oscillation. That means if oscillation occurs, then what should be happening in terms of these component values, what should be their values so that oscillation occurs. So we will now have to find out these two quantities, A and beta, and then set up this equation 5 and solve it for the possibly oscillation frequency and some other condition. So actually there are two equations, so there will be two informations that will be extracted out of this equation 5. So here it is easy to find out A, because A is simply a non-inverting amplifier. So we know that A is simply 1 plus the negative feedback resistor divided by R1. So this is known, this is easy. Now we have to find out what will be beta, right? So to find out beta, we have to use this network. So you can see that this network is basically doing the voltage division. Here we can see that there is a series impedance ZS, and there is a parallel impedance, and these two, they are dividing this output voltage to produce the feedback voltage. So here what we have is ZS is simply R plus 1 by j omega c, that means 1 plus j omega c r divided by J omega C. Similarly, Zp can be found out to be R divided by 1 plus J omega Cr. So these two, they produce the feedback voltage Vf as Zp divided by Zp plus Zs into Vo. And this A is basically Vo by Vf. So from here we find beta is equal to Vf by Vo is Zp by Zp plus Zs. Now from 6 and 7 we find A into beta is 1 plus R2 by R1 into Zp by Zp plus Zs is equal to 1. So here we can find out what will be Zp by Zs. So if we find out Zp by Zp plus Zs, this factor, if we calculate it separately, this will turn out to be 1 divided by 3 plus J omega Cr my plus 1 by J omega Cr. Right. Or this can be written in terms of negative sign like this. Yeah. So now we can implement the Burkhausen criteria. That means we can write this thing in more explicit form. Yeah. So here we will use the magnitude and phase part of magnitude and phase version of the Burkhausen criteria to attack this equation. So it says that magnitude is beta A is equal to 1 and phase is beta A is equal to 0 degree. So if the phase of this term is to be 0, then that means it has to be purely real. And purely real factor can be obtained, or this can be converted in purely real if the denominator of the second part, that means this is real. So you can say that for beta A is phase to be 0, or even the whole factor to be real, this denominator imaginary part must vanish. That means omega Cr minus 1 by omega Cr should be equal to 0. So this implies omega square is equal to 1 by Rc. That means omega should be equal to, sorry, this should be Rc square, Rc. So this is the frequency at which Birkhausen criteria will get fulfilled. So only at this frequency we will get output, even in absence of any external input. Now, so we have already used this part, the phase part. Now let us see that what this implies then. So we see that this equation, which is the expanded equation 8, expanded version of Birkhausen criteria. So this and 9. So equation 8 from 9 implies 1 plus R2 by R1 into 1 by 3 is equal to 1. So this is 1 plus R2 by R1, which is the gain of the non-inverting amplifier, should be equal to 3, or R2 by R1 is equal to 2. So oscillation will occur at this frequency, omega is equal to 1 by RC, and the gain at that point is going to be equal to 3. Now let us try to see that why gain should be 3. And why at this condition, that means when gain is 3 and frequency is 1 by RC, oscillation will occur. So here we can see that this factor in the equation 8, second factor is basically this Zp by Zp plus Zs. So the RC circuit, basically what it does is, this is Zs, this is Zp, and it is sensing VO and it is producing VF, which is VO by 3. Because here you can see that when this imaginary part is 0, this factor is simply 1 by 3. So Zp and Zs together produce 1/3 of the output, and it is this thing which is fed to the op amp. So now you can see that what is happening here is 1/3 is being fed to op amp in this way. So that means what op amp should now do, or this part of the circuit which is going to act like an amplifier, it should multiply that signal by 3 so that we land up to the exactly same signal from where we started. So we started with VO, we took out 1/3 of the VO, and then we set up a circuit. What it does is that this circuit is that it multiplies that VF, that means VO by 3, so that ultimately you get the same signal. So you can see that at this frequency 1 by RC, the 1/3 of the output will be taken and then it will be multiplied by 3 so that we get the same output. And in this way, this phenomena will continue forever under ideal condition. Now we will see that why this circuit is also called bridge, and we will try to use the property of a bridge to derive the oscillation condition. We will arrive, you will see the same equations. So we are going to focus now on the bridge aspect. So we know that in a bridge there are 4 arms. Each arm consisting of one impedance. Suppose here we have already defined these 2 voltages. Then under the balance condition, the voltage of VE will be equal to VF. So there will be impedances here, 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 here. So they all will be equal. So now we are going to put the impedances. Here we will put R2, here we will put R1, here we will put series combination of R and C, and here we are going to put parallel combination of R and C. So we will keep it more general. We can take R3, C3, R4, C4, right? And then we will put op-amp here. So the same circuit that was shown earlier has now been uh, represented in the form of bridge. So we again here have parallel and series impedances, ZS, and here ZP. So this is the condition for balanced bridge. So we have to find out VE and VF, and let me write ZS 1 plus J omega C3 R3 divided by J omega C3, and ZP as R4 divided by 1 plus J omega C4 R4. So we know that these voltages VE will be given by this equation, R1 divided by R1 plus R2 into VO, and VF as ZP divided by ZP plus ZS into VO. Now we know that under the balanced bridge condition, this equation 10 is going to be valid. So from 10, we get R1 divided by R1 plus R2 is equal to ZP divided by ZP plus ZS. We have already cancelled out, and from here we can find that R2 by R1 will be equal to ZS by ZP. Right, so now we can substitute ZS by ZP, and that will give rise to 1 plus J omega C3 R3 divided by J omega C3 divided by R4, 1 plus J omega C4 R4. So we can simplify this, and this will give us one minus omega square C3 C4 R3 R4 plus J omega C3 R3 plus C4 R4 whole divided by J omega C3 R4. So this is, let us say, equation 11. Now here we see that this left hand side is real. So this right hand side should also be real. So this also should be real. So that we can say can be made real easily if this factor, the first two terms on the numerator on the right hand side, they become 0. Then J omega from numerator and denominator will cancel out. So for right hand side also to be real, what we find is that 1 minus omega square C3 C4 R3 R4 should be equal to 0. So this implies omega square is equal to 1 by C3 C4 R3 R4. And now if you take C3 is equal to C4, R3 is equal to R4, then we find that we arrive at the same equation that we arrived from the feedback model analysis. Now once the equation 11 is say, or right hand side of 11 is real, then equation 11 reduces to R2 by R1 equal to C3 R3 plus C4 R4 divided by C3 R4. Yeah. So this will become R3 by R4 plus C4 by C3. Right, so in this case, the gain, which is 1 plus R2 by R1, will become equal to 1 plus R3 by R4 plus C4 by C3. And here also for R3 is equal to R4, C3 is equal to C4. What we get is the gain 1 plus R2 by R1 will become 1 plus 1 plus 1. That means 3. So we arrive at the same conclusion that we obtained from the feedback model. So this is a Wien bridge oscillator. In fact, this is one of the very popular oscillators. And in fact, this was one of the first product that HP launched as a signal generator. It was this Wien bridge oscillator which they had used. Now we are going to talk about another circuit which again consists of R, C and an op-amp, and this one is called phase shift oscillator. So here we will see that this oscillator also basically works based on the same principle. That means Burkhausen criteria. But here I would like to point out one fact for the Wien bridge oscillator, because it is actually that fact which appears as a page in the name of the second circuit. So here what we find is that Burkhausen criteria says that phase of beta A should be equal to 0 or 360 degree, right? So we can see that this phase, total phase, will be actually contributed by phase of beta and phase of A, that means amplifier. So if we have a circuit where the amplifier is not contributing any phase, that means it is adding 0 phase, then beta network should also add 0 phase. And that is what is happening here in the Wien bridge oscillator. Because here you can see that this is a non-inverting amplifier. That means when signal travels from this input to the amplifier and reaches to the output, phase is 0 degree. So here the phase of A is equal to 0. That means now the phase of beta should also be equal to 0. So Burkhausen criteria says that this is also equal to 0 or maybe 360 degree. And that is why we see that only at omega is equal to 1 by RC, this network will produce a feedback signal which will have a 0 phase. That means output, this output and this output, they will be in same phase. So here we won't have to worry about the phase. We just ensure that their product beta A into A is equal to 1. But now we are going to set up a circuit where the amplifier will be basically used in inverting mode. So let me first draw the circuit of this phase shift oscillator. So whether we use amplifier in inverting mode or in non-inverting mode, topology remains same. Only difference is whether there is input here or here. Based upon that, the same circuit, this circuit will act like inverting mode or non-inverting mode. So recall for Wien bridge, this point was grounded, and that is why it had become non-inverting amplifier, because input was at this location. But now what is happening is we are going to give input at this location, and this positive terminal is going to be grounded. So this is going to be in inverting mode. So this implies that phase of this is going to be 180 degree. So now there is going to be a network which will take a signal from output and feed to this part. So that is why this phase word has become important in the title of this circuit. So this network is different from what was used for the Wien bridge. Now let me draw this network also. So what we want is, you can see that because this amplifier is already producing 180 degree phase, that means this network that we will put here, that should also produce a phase equal to pi, right? So to fulfill this requirement only, we have this RC network. So in general, all these C and R, they could be of different value, but to keep the analysis simple, we are going to take each of them to be of same value. And we are going to make some modification here. We will keep this R2 as RF and R1 as R, right? So here you can see that we have a sort of three RC circuits. This is one RC circuit, this is another RC circuit, third is this one. So we have three RC circuits. So question will arise why we need three RC circuit. Objective is clear that we want 180 degree phase shift from the beta network, which we are going to use from RC. So this is what we are doing. We have C, we have R. So here this output is being fed to the another output. So here you can see that VO is going to be R divided by R plus 1 by G omega C. That means G omega C R divided by 1 plus G omega C R VI. Right. So VO by VI is G omega CR divided by 1 plus G omega CR. Now if you see the phase of this quantity, because we are connecting primarily this RC network for the purpose of achieving total of 180 degree phase shift. So we have this network, so this is going to phase of G omega CR numerator minus phase of denominator. So this phase is going to be pi by 2 minus tan inverse omega CR. So this phase is going to be frequency dependent because of this, and maximum phase will occur for omega is equal to 0, and this is going to be 90 degree for omega is equal to 0. And when omega is infinite, this phase is equal to 0. So we see that maximum phase that we can get out of it is equal to 90 degree, and we needed a total of 180 degree. So two of such networks can be used, but we see that they will be able to offer 180-degree phase shift only at zero frequency. That means at DC. So this will not be useful if you want oscillation to take place at some other finite frequency. And that is why we had to include three such networks so that their maximum is more than 180 degree, and there will be possibly a frequency where their phase shift will become 180 degree, and that is why three such networks have been used. Now, for the analysis purpose, we will redraw the circuit. This is RF, and here we have CR, CR, CR. So this R which was here at the inverting input, that has been brought here with the C, so that we can clearly see three RC networks. Right. So in this case, clearly the A is VO by PF, and this is going to be minus RF by R. Right. No, sorry, there is a mistake here. This is not connected in this way. Rather, it is connected in this way. Here. But here we see that a negative feedback exists between output and this, so that implies virtual short. Short exists, that means this node is grounded. That means equivalently this node is also grounded. So this we have sort of decoupled these two things. VF is this term voltage. So A is known, VO by VF is equal to minus RF by R1. So what we have to find out is beta is equal to VF by VO. This is what we have to find out. Then we can set up the Burkhausen criteria. So for that, we will have to carry out analysis of this RC network. And there are actually three loops. And we will assume currents in each of these three loops. And then we will set up an equation using KVL in the three loops, and there will be three unknowns. So here we have three unknowns, I1, I2, I3. So we can use mesh analysis. So this will imply three equations, and in I1, I2, I3, and those three equations, they now have to be solved for VO by VF. So let us write these three equations. First is KVL in loop 1. So here we have voltage VO. So we can write KVL in this direction. So that will give rise to minus VO plus XC I1 plus R into I1 minus I2 is equal to 0. So through this R, we have current I1 and I2 both flowing, and XC is impedance offered by one of the capacitors. So XC is 1 by j omega C. So this is for KVL in loop 1. So this will simplify to minus VO plus R plus XC I1 minus R I2 is equal to 0. So here we have two unknowns I1 and I2. Now we need to write two more equations for I1 I2. So we write KVL in loop 2. So that will give rise to R into I2 minus I1 plus ZC I2 plus R into I2 minus I3 is equal to 0. So here we see that we have I1, I2 and I3. All three are present here. So this will simplify to minus R I1 plus 2 R plus XC I2 minus R I3 is equal to 0. So this is, let us say, equation 12. This is 13. Similarly, in loop 3, if you apply KVL, you will finally get minus R I2 plus 2R plus XC I3 is equal to 0. So we have three equations and three unknowns, right? And we can eliminate these currents, and keeping in mind that VF is R into I3. So this is how VF will come into the equation, and VO is already there present in the equation 12. So ultimately, when we eliminate each of these unknowns, we will get an equation containing VO and VF. And using all these equations, what we will get is minus VO plus 1 plus 6 by j omega CR minus 5 by omega C square R square minus 1 by j omega cube C cube R cube. This whole thing is going to get multiplied by VF and equal to 0. So this elimination is going to be a little bit lengthy, right? So here we find that this factor appears everywhere. It's a square, it's cube. So we can call this as, say, omega CR as alpha. So this will get simplified to VO minus VO plus VF into 1 plus 6 by, let us call this as omega alpha, to 5 alpha square minus alpha cube by j is equal to 0. So from here we can find out beta as VF by VO, and this will be 1 by 1 minus 5 alpha square plus 1 by j into 6 alpha minus alpha cube, right? So this is beta, and A we already know is RF by R, and this is real. So this in general is complex, beta is complex, right? So we know that beta A should be equal to 1. That means it should be real, or phase of beta A is equal to 0 degree. So that will happen only if beta is also real. So we see that beta is complex because of the second factor in the denominator. So for beta to be real, the second factor in the denominator, that means 6 alpha minus alpha cube, this should be equal to 0. And since alpha cannot be 0, it will be 0 only at omega is equal to infinity. So 6 minus alpha square is equal to 0. That means as square root 6. Now alpha is 1 by omega RC. So this implies omega will be equal to 1 by square root 6 RC. So this is the frequency at which beta will be offering 0-degree phase shift, and this will be the frequency at which oscillation will take place. So now we have to find out what should be the gain, that means RF by R. So here for this frequency, beta, we can see from this equation, will get reduced to 1 by 1 minus 5 alpha square. So beta becomes 1 by 1 minus 5 alpha square, that means 1 minus 5 into 6 is equal to minus 1 by 29. So this will be the value of beta at oscillation frequency. Now at the above oscillation frequency, what should happen is beta A is equal to 1, and beta we have found out to be minus 1 by 29. A is minus RF by R is equal to 1. That means RF by R should be equal to 29. So that means the gain of the inverting amplifier is going to be 29. So if you set up the above circuit with gain is equal to 29, then this circuit will oscillate. If it oscillates, that means if it produces output, it will produce output at omega is equal to 1 by RC. So this phase shift oscillator was taken from Cedar Smith